So, hello and welcome to this video here. Today, again, we're going to talk about least squares methods. And this time we're going to see two small applications to real-world data and some more examples of how to model functional correlations. We'll have a look at linear and quadratic models, and we'll also have a look at a logarithmic approach. So let's first have a look at our two problems. We'll have a look at the per capita beer consumption in Germany over the years. And we also have a look at the per capita coffee consumption in Germany over the years. And we'll see how we can model those as a function of the year of time and how those develop over time. So let's first have a look at the data for the beer consumption. So here's the year. You can see I have the years here. I have the corresponding data. That's the per capita consumption in liters. And you can see that increased quite a lot over the first few years here, from 1950 to 1990, 1980. And then it started to decrease a little and almost stayed constant over the last few years. I normalized the time scale, first thing, to start from 0. So 1950 is considered as year 0. And then T is 10, 20, 30, and so on, meaning 1960, 1970, 1980, and so on. I mainly did this for numerical reasons. I'll upload the worksheet that you can see here so that you can do your own experiments. Feel free to try to work with the actual years and see how that changes the outcome. It will change it slightly. Now, if you have data like this, the first thing you probably want to do is have a look at the data. So meaning I plot the data. So here's the raw data as an array. I'm using Python and the NumPy package to process that data. You don't really have to know Python and the NumPy package. It's just about understanding what happens mathematically in the background here. But again, if you want to experiment with this for yourself, feel free to do so. You can just take my code and change it to adapt it to your needs. So here's the scatter plot of the beer data. You can see here's the first point, those points here. So that seems to suggest not really a linear correlation, but still we'll give a linear model a first try, simply because it's easy. Linear model means the consumption is modeled as a function of the time t. So we have some parameter alpha times t plus some other parameter beta. And we can translate this into matrix vector form like this. So this is our alpha column, meaning we have 0 times alpha, 10 times alpha, 20 times alpha, right? And so on. That's the t. Here's the beta column. We have 1, 1, 1, 1, 1, 1, and so on for the beta. So A times alpha beta is equal to B. That's the system of linear equations that we're trying to solve. Now this is an infeasible system, as you can see from the scatter plot. So we're going to find a least square solution. And we do this by solving the equation A transpose AX hat equals A transpose B. Again, we're not going to do this by hand. We're going to let Python do the work for us. Here's the Python notation for what happens here. So we solve a system of linear equations. This add here, this is the notation for matrix multiplication in Python. And this is the result, the array X that we get. This first here is the parameter alpha. That second is the parameter beta. So if we plot this into the data, then we get this line here. And you can see this first point is way off the line, and also these points above here, those are way off the line. So it's not a very good approximation. Maybe if you look at the data, that seems to suggest more like a quadratic correlation. So let's try that next. Let's try a quadratic model. That means our consumption is modeled as a function with 3 parameters now. We have alpha times t squared plus beta times t plus gamma. Now, if we write this in matrix vector form, the matrix gets one more column. So we have this first column corresponding to t squared here. Means we have 0 squared, 10 squared, 20 squared, and so on here. The second corresponds to t, so we have 0, 10, 20, 30, and so on. And the third corresponds to 1 times gamma, so we have 1, 1, 1, and so on. Right-hand side stays the same, of course. Now what do we get if we do the same computation? After a little more work, this is the output. So we get these 3 parameters here. And here's the plot. And as you can see, this quadratic model is a much better fit for the data. One thing to note is that the recent data here, that seems to be fairly constant. So that does not quite support the quadratic model. The consumption in the quadratic model would go down here and in the future considerably. So we might have to adapt this to get a better model. But that is actually something that you can try to experiment for yourself. I'll show you in the coffee consumption problem how to do a different model. So let's have a look at the data of coffee consumption once again. Same years. This is the coffee consumption per capita in kilograms. And you can again see that increased considerably, and then it stayed almost constant with little deviations. So here's the scatter plot once again. Sharp rise, and then it's getting almost constant. So around 7 kilograms. The data doesn't seem to change a lot anymore. Still, let's try a linear model first, just to see how it's done. The matrix A is the very same as before. What changes is, of course, the right-hand side, so different B. Again, the computation, same as before. We get these parameters, and if you plot that, we get this line here. And you can see that's not a bad fit at all. So here's some points that are way off the line, but still, it seems to be not too bad. But of course, with the recent data suggesting more of a constant level of consumption, the predictions will probably not be very good. So let's see if we can do better. Let's try a quadratic model. Again, we've used that before. We introduce a quadratic term. So we have a matrix that now has 3 columns, 1 for each parameter, alpha, beta, gamma. Computation is the same as before, and here's the result that we get. And you can see this models the growth fairly well. And then it's pretty flat, so it's also not too bad. But in the future, it will go down again. So maybe it's not a very good predictor. One other possibility here that we will try now is we have a function with a sharp growth and then it levels off. So that seems to suggest there could be a logarithmic behavior here, right? Sharp growth first and then leveling off, almost staying constant. So let's try a logarithmic function. For this logarithmic model, the idea is to model the consumption as alpha times a logarithm. I'm just using the natural logarithm plus the constant term beta. And you notice I used logarithm of t plus 1. That's mainly for technical reasons. In my data, the year count starts at 0, and there is no logarithm of 0, so that wouldn't work. That's why I'm using t plus 1 here, so that internally the model starts at 1. So what's the matrix corresponding to this? Well, simple. What we get is, again, alpha, this first parameter, corresponds to the first column. And in that first column, we simply have this expression here for all the t's. So here is ln 0 plus 1, ln 10 plus 1, ln 20 plus 1, and so on. And the beta corresponds to the second column. It enters every equation with 1, factor of 1, right? So that's the corresponding matrix. Right-hand side is again RB. And the computations are again the same. We still need to solve this equation here. And this is what we get. You can see this is 1.72. The second parameter, the p, is very small. Notice there's a e-04. That's a short for times 10 to the power of -4. So it's really small here. And that's the plot that we get if we plot this data here. So you can see there's a sharp rise. That's fit pretty well in our model. These are a little off, but then for the current points, that seems to fit fairly well. So that might be a good model. To see if that model really works, you can try to find the latest data for coffee and beer consumption and see what values these models would predict for 2019 or 2020, and then compare that to the real data. Of course, keep in mind that 2020 might be a bit different in several aspects, and maybe beer and coffee consumption are one of those aspects where the year is unusual, let's say. So 2019 might be a better data point if you want a comparison. And of course, feel free to tweak these models and see if you can find better approximations. So this demonstration concludes our introduction into least squares method. And actually, it concludes our introduction or overview of linear algebra methods for now. Next we'll do is we'll start diving into the realms of analysis, real analysis. And this is going to be the topics of the upcoming videos. And as usual, I'm very confident I'll see you then.